Okay, so today our goal is to study about the chemical kinetics. So we are going to start with the chemical kinetics. This is all about the reading NCRT point wise. Okay, because in every competitive exams, whether it is neet or JE, whatever neet or JE, it will be useful the reading the NCRT each topic line by line, because statement wise question, assertion reason question, they will ask directly from the NCRT only. So it is very important to read the NCRT. So today we are starting with chemical kinetics. Okay, today's goal is to finish the chemical kinetics. Half an hour we will go with the reading the NCRT line by line. Half an hour, how much we can cover, that we will cover today. Okay. So before starting with this one, I just want to say you that, see what all we will cover in this chapter. First we will study with the kinetics. Okay, so in kinetics what we are going to study about the rate. Means kinetics means what? Actually kinetics, it is the speed. It talking about the speed. When we say about the speed, we know the distance by time. It is distance by time. So definitely this distance is, when we talking about the physics or something else, distance by time, that is change. What we are changing is distance. Okay, so that change in the reactions is actually kind of observable properties like concentration or something else like color, anything, pH, anything. It can be some observable properties which is changing upon time. Okay, so those within this time, how much has been changed, what is the rate. So this chemical kinetics is going to talk about this all. So what all we will cover in this chapter, whenever you are starting the chapter, be ready with that. You have to aware about what all are there in the chapter. For example, we will study about the rate. Okay, what is rate, what is average rate, and differential rate. Okay, differential rate and integrated rate. Okay, integrated rate, then its time related equations and all, and about the temperature dependence like Arrhenius theory. Then last one is about the catalyst. Okay, catalyst. So these all we have to cover in this particular chapter. So before starting with the chapter, definitely we have to know that which all we are going to study in that particular chapter. What is the goal of the chapter, you should know. So let's start with this. Okay. So, chemistry by its very nature is concerned with change. Substances with well-defined properties are converted by chemical reactions into other substances with different properties. For any chemical reaction, chemists try to find the feasibility of a chemical reaction, which can be predicted by thermodynamics. As you know that the reaction with delta G less than 0 at constant temperature and pressure is feasible. Okay, so for any chemical reaction, chemists try to find the feasibility. Means they tried whether it is possible or not. Okay, now in order to whether if the reaction is possible, its delta G has to be less than 0 spontaneous, we know. Okay, correct. Extent to which a reaction will proceed can be determined from chemical equilibrium. Okay, we know if chemical equilibrium equilibrium constant is very large, 10 to the power 5 and all, very large, we can know that almost the reaction, we know that K equilibrium is equal to product concentration divided by reactant concentration. So if it is very large, product concentration is more, right? Product concentration is more, which means that the reaction is almost ready to complete. Okay, so the extent of which a reaction will proceed can be determined from chemical equilibrium. Speed of a reaction, that is time taken by a reaction to reach equilibrium. So speed of reaction, it is all about the chemical kinetics. Okay, so these things are chemists observed to find out. Okay, along with feasibility and extent, it is equally important to know the rate and the factors controlling the rate of a chemical reaction for its complete understanding. In order to understand it completely, like its mechanism and all, it is very, whether it is feasible or not, we can, for example, I will say an example, carbon, graphite, or carbon diamond, if you take, we know that carbon graphite is thermodynamically more stable one, so carbon diamond should come convertible to the carbon graphite according to thermodynamics, right? Its delta G is less than 0. But the thing is that it will take in years of years, right? Because its kinetics is very slow, its speed is very slow. So whether the reaction will takes place or not, according to thermodynamics that will takes place, but according to kinetics will not. It take a long years of time, right? So for example, which parameters determine as to how rapidly food gets spoiled? Exactly. See, in the food industry, like whether food gets spoiled or not, it is like said by, like for example, how much time long, like life of that food, how much time it can be stored. Already, like those all are determined by the kinetics. How to design a rapidly setting material for dental filling? So when you fill whatever used in the dental filling, how long it will stay there, okay? Or what controls the rate at which fuel burns? What control? Okay, the rate at which the fuel burns in an auto engine, okay? So the rate, how feasibly or how fast that can be used in it, like for or what controls the rate at which the fuel burns in an auto engine, okay? What controls the rate at which, okay, like how fast the fuel is burning in that auto engine, like your automobiles and all these questions can be answered by the branch of the chemistry which deals with the study of chemical kinetics, okay? Like deals with the reaction rates and their mechanism, that is chemical kinetics. The word kinetics is derived from the Greek word kinesis, meaning movement, okay? Thermodynamics tells only about the feasibility, of the reaction, whereas chemical kinetics tells about the rate of the reaction. Thermodynamics tells feasibility, chemical kinetics tell about the rate. For example, thermodynamic data indicate that diamond shall convert to graphite, but in reality the conversion rate is slow, that the change is not like perceptible at all, okay? Therefore, the most people think that diamond is forever, okay? Most people think that whatever I have already said, that is only this, okay? Kinetic study not only help us to determine the speed or rate of a chemical reaction, but also describe the condition by which the reaction rates can be altered, okay? So kinetics not only helps us to determine the speed or rate of a chemical reaction, but also describe the conditions by which the reactions rate can be altered, what all you can do to that reaction to alter the speed. For example, adding catalyst and all, okay? The factors such as concentration, temperature, pressure and catalyst affect the rate of the reaction at a microscopic reaction, okay? Now at a microscopic level, we are interested in the amounts reacted or formed and the rates of their consumption or formation. At the molecular level, the reaction mechanism involving orientation and energy of the molecules undergoing collisions are discussed. See, at the not microscopic levels, macroscopic level, what we can observe, that depends on like amount reacted or formed on and the rate of the consumption. These all are observable thing. But molecular level, which we cannot observe, is the reaction mechanism involving orientation. For example, inside the reaction, the molecules, whether it is coming in the proper orientation, like for example in SN2 reaction, you know, the molecule has to come from the backside of the leaving group. So the proper orientation, molecular level also, the rate of the reaction or the mechanism of the reaction can also be observed by knowing the kinetics, okay? In this unit, we shall be dealing with average and instantaneous rate of a reaction and the factors affecting, okay? Instantaneous rate means at an instant, okay? Average means at an interval, two interval from 10 minute to 15 minute, what change is observed, that is average. Suppose instantaneous rate, where is that instantaneous rate? In this lesson, like we will say instantaneous at 10 minutes, at instant, at that particular time what is happened or how much the reaction has been consumed, that will be also studied. Some elementary ideas about the collision theory of reaction rates also given. However, in order to understand all this, let us first learn about the reaction rate. Okay, collision theory also we will talk about. Okay, rate of a chemical reaction. First thing, rate of a chemical reaction. Some reactions such as ionic reactions occur very fast. Okay, so make a note that ionic equations are very fast. For example, precipitation of silver chloride occurs continuously by mixing of aqueous solution of silver nitrate. Okay, any ion silver nitrate AgNO3, if you take mixed with silver chloride, that is AgCl, will be like precipitated out from the AgNO3 when you mix it with sodium chloride. Okay, so that is a very fast reaction. On the other hand, some reactions are very slow. Which are the very slow? Here they have given, for example, rusting of iron in the presence of air and moisture. Also there are reactions like inversion of cane sugar and hydrolysis of starch, which proceeds with a moderate speed. Okay, so these all are the like of reactions. You know, ionic reactions are very fast, and rusting of iron is very slow, and moderate is hydrolysis of starch, cane sugar, etc. moderate, which proceed with a moderate speed. Can you think of more examples from each category? Okay, let's see. You must be knowing that speed of an automobile is expressed in terms of change. You must be knowing that the speed of an automobile is expressed in terms of change in position or distance covered by it in a certain period of time. Okay, similarly, the speed of a reaction or the rate of a reaction can be determined as the change in the concentration of reactant or product in unit time. To be more specific, it can be expressed in terms of like automobiles distance, like 1 kilometer per second, like that we are saying 10 kilometer per hour, like that all we are saying, like there is like how much has been concentration changed per hour, per minute. That is comes about the chemical kinetics. The rate of decrease in concentration of any one of the reactants, suppose reactant is converting to product, rate of decreasing in the reactants or the rate of increase in the concentration of one of the product will increase, the rate at which it increase. Okay, consider a hypothetical reaction assuming that the volume of the system remains constant. Volume of system remains constant. Volume is remaining constant. Why? Because volume in a container reaction is happening, the volume has to remain constant. Then only we can take directly the number, because concentration is equal to N by V. Okay, if the volume is constant, concentration is directly proportional to number of moles. Okay, so assuming that the volume of the system remains constant, reactant converting to product, 1 mole of the reactant are produces 1 mole of the reactant R produces 1 mole of the product. If R1 and P1 are the concentration of R, P respectively at time T, okay, time T1, okay, and R2 and P2 are their concentration at time T2. Okay, so T2, the reaction is moving from T1 to T2. Okay, now delta T will be equal to T2 minus T1, delta R is equal to R2 minus R1, delta P will be equal to P2 minus P1. The square brackets in the above expression are used to express the molar concentration. So when it is expressed like this, it is concentration of P. Okay, rate of disappearance of R, how fast the reactant is going to disappear, that is told by decrease in the concentration of R divided by time taken. Okay, so minus delta R by delta T. Okay, so now why there is a minus sign in that? Okay, listen here, why there is a minus sign there? Minus sign is because rate is always positive. Rate is positive quantity. Okay, rate means it is saying about the speed, it is always positive. So rate of disappearance, see, initially 2 concentration, changing to 1 concentration, reactant, okay, reactant is consuming, initially 2 mole, changing to 1 mole. So like change will be, delta R will be final minus initial, right, final minus initial, that is 1 minus 2, this is coming to be minus 1, sorry, minus 1, right. So minus 1 is a negative quantity. To avoid that negative quantity, we will already like mention here as, here we will mention like minus, so minus of minus 1 will be positive, right. So that is why we are introducing a factor minus to mention this decrease, okay, to mention the decrease in the concentration only we are using this sign here. Now rate of appearance of P, rate of appearance of P is equal to increase in concentration of delta P divided by time taken, delta, so it is increase, so we will mention like positive. Since delta R is a negative quantity, R is a negative quantity, as concentration of reactant is decreasing, it is multiplied with minus 1 to make the reaction a positive quantity, okay. Equation 3.1, which was that delta R by delta T, okay, and 3.2 give like where it is 3.2 given above present the average rate, because it is between a time interval, okay. So average rate of a reaction, that is R average, okay. Average rate depends upon the change in concentration of reactants or products and the time taken for that change to occur, okay. So instantaneous and average rate of a reaction, you can see here there is a graph given which is instantaneous and average, okay, this is given average. You can see that when you, this is R, okay, and this is a time t, so R initial concentration is this one, okay. So R is decreasing, concentration of reactant is decreasing over time, so at a particular interval T1 and T2, okay, T2 is not here, T2 is here, okay. At T1 and T2 we are taking that change, and this slope we are taking, this slope, okay. So that slope, that is here, this will give the R2 minus R1 and this will give the T2 minus A1. So if you take the slope, that is dx by dt, you know, sorry, dy by dx is the slope of the graph, we will get delta R by delta T, okay. So this minus sign will come because it is positive, okay. The slope, you can see it is positive, negative only, slope is negative, okay. Now instantaneous rate, instantaneous like how will you get an instantaneous rate? Here we got the difference of R2 minus R1, T2 minus T1 we took, divided by T2 minus. To get an instantaneous rate at T only, right? T, you have to get the slope of this line. So at T, you will take the slope of the line, that is d minus dr by dt, you will get the instantaneous rate. So this is against the concentration of product, which will be having a positive, like positive slope, because the concentration of the product will increase over the time, okay. Product will increase over the time. The same concept has been applied here also. Now unit of rate of reaction, okay. From equation 3.1 and 3.2 it is clear that units of rate are concentration per time, because concentration delta R, it is concentration divided by time, okay, delta T. So concentration per time, rate of the reaction, unit is concentration per time. For example, if concentration is in mole per liter and time is in second, then units will be mole liter inverse second inverse, okay. Mole per liter is the concentration, time is the second inverse. However, in gaseous reaction, when concentration of gas is expressed in terms of partial pressure, the units of their equation will be atm second inverse. So the rate can be same time mole liter inverse second inverse. Also it can be atm second inverse, okay. That's what we are saying, okay. Now next part, it can be seen from 3.1, it can be seen from table 3.1 that the average rates falls from 1.9 into 10 to the power minus 4 mole second inverse to 0.4 into 10 to the power minus 4, okay. Table, this one I guess, yeah. From here it is okay, from here to here it is falling. Okay, however average rate cannot be used to predict the rate of a reaction at a particular instant. Okay, that is saying by instantaneous rate, as it would be constant for the time interval for which it is calculated. Okay, okay, yeah, see, this particular time interval I am taking from 0 to 50, it is having a rate constant, or this is r rate. Average rate is this much only. For this time interval it will be this only, so it is constant at a time interval. Okay, so it is, so to express the rate at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say when delta t approaches to 0. Means the delta t 50 0 point, it should be approached to 0.0001. So at a particular moment, it has to very close to that interval is very small, then it is instantaneous rate. Then hence mathematically, for an instantaneous infinitesimally small dt, instantaneous rate is given by r average is equal to minus delta r by delta t is equal to delta p. See why it is equated? Because the rate of the reaction, whether it is respected with the reactant or whether it is respected with the react product, it should be same only, right? So that is why it is equated. As delta t approaches 0, r instantaneous is equal to minus dr by dt when it is approaching to 0. So here we know, this is what we have already seen. Slope, suppose we have to find the instantaneous rate at time is equal to 600, then we have to take the slope of that 600 where the graph made, then we will get the instantaneous rate. Is there anything in this other than that? Okay, instantaneous rate of hydrolysis of butyl chloride. Hydrolysis of butyl chloride only they have given here. Other than that, there is nothing important with this. Okay, fine. It can be determined graphically by drawing a tangent at time t on either of the curves for concentration of r and p versus time and calculating its slope. So in problem 3.1, it's just instantaneous rate calculation, it must be, we'll check it. R instantaneous at 600 second, for example, can be calculated by plotting concentration of butyl chloride as a function of time. A tangent is drawn that touches the curve at t is equal to 600 second. The slope of this tangent gives the instantaneous rate. Okay, so r instantaneous at 600 second is equal to minus of, means it is represented with terms of the product. So let's check that data. At 600 second, table 3.1, 600 second, where it is 600 second, 0.01, okay, 800. Okay, at 600 second, you can see here from this graph. Okay, at 600 second, okay, I have drawn this one, it is reaching at this point. So what is y-axis touches here and x-axis touches, y-axis touches here as well as here, and x-axis touches 400 and 800 interval. So slope of the line will be y, delta y by delta x you can take. That's what they have taken here. 0.0165 minus 0.0037 at 800 second. Where is 800? At 800, this will be approximately 0.017, and at 400 it will approximately 0.03 something, I guess. Okay, so that's what they have did, and they will get the instantaneous rate at that particular point. At 250 second they can calculate like that. All things that they can calculate like that. Now consider a reaction Hg plus Cl2 gives HgCl2, where stoichiometric coefficients of the reactants and products are same. Okay, stoichiometric coefficient of the reactants and product 1, 1, 1. Okay, same. The rate of the reaction is given as minus delta Hg by delta T is equal to minus delta Cl2 by delta T delta HCC. Formation of rate of deformation of reactants will be equal to rate of deformation. All the reactants are equal to rate of formation of the product, because rate of the reaction has to be same for even if we go with the reactant or product. Okay, now Rate of disappearance of any reactants is same as the rate of appearance of the products, but in the following reaction 2 moles of 2 moles of HI decomposes to produce 1 mole of each of H2 and I2. For expressing the rate of such a reaction where stoichiometric coefficients of reactants or products are not equal to 1, the rate of disappearance of any of the reactants or the rate of appearance of the product is divided by the respective stoichiometry coefficients. Since the rate of consumption of HI is twice the rate of formation of H2 or I2, to make them equal, the term delta HI is divided by 2. The rate of this reaction is given by, okay, so this is always, see, the rate of the reaction has to make the equal. So in order to that, they are dividing that equation or that rate divided by its stoichiometric coefficient. For example, I will just say here an example. Okay, listen here. A is converting to 2B. Okay, A is converting to 2B. Initially 1 mole was there. Initially suppose some X mole is there. Okay, suppose some X mole is there, and from X mole 1 mole dissociated, then 2 mole has to formed. Okay, not initially, I'm saying if 1 mole has been dissociated, 2 moles has to be formed according to the stoichiometry, because according to mole concept we can say that 1 mole of A will produce 2 moles. So 1 mole dissociated, it will produce 2 mole. Okay, right? So I can say that rate of deformation or rate of formation of B when 1 mole when 1 mole of A has been dissociated, 2 mole of B has been formed, which means that rate of formation of B is equal to twice of rate of formation of A. Okay, I am just taking rate of formation as A only, twice as rate of formation of A. That is means here when 1 mole dissociated, 2 mole has been formed, so it is twice. Rate of formation of B is twice. So I can say that rate of formation of B, that is dB, okay, by dt is equal to twice of rate of B formation, that is minus dA by dt. Okay, so if you in order to make it equal, I can also say that this twice you can put it here. See, if you put it here, plus dB by dt, 1 by 2 will be equal to minus dA by dt. So this is same, right? See, same what we are doing here. See, here what they are doing, here they are just, it was 2, it divided by 2. Here it was 2, where is B? Okay, here it was 2, we also divide it, so he also dividing it. That's what they are just taking to make it practically the same thing only they are saying. Okay, so the rate of the reaction here is minus 1 by 2 delta H by delta T is equal to delta H2 by delta T, I2 by delta T equal to. Okay, similarly for this reaction we can see that deformation minus 1 by 5, BrO3 constant is stoichiometry is 1, so it is minus 1 only. Here minus 1 into BrO3 by delta T, here it is 6, so 1 by 6, here it is 3, so 1 by 3, here it is 3, so here also 1 by 3 to make it equal. For a gaseous reaction at constant temperature, concentration is directly proportional to partial pressure of a species, and hence the rate can also be expressed as rate of change in partial pressure of the reactant or the product. See, instead of taking reactant, see, I told you rate can be expressed in any terms, any changing terms, concentration changing, pressure changing, pH changing, color changing. Rate can be expressed in any term. So for gaseous reaction, more observable thing is pressure changing, right? So because of that, for a gaseous reaction we will take partial pressure of the reactant or product. Okay, so it's almost time. See, we will just check that example what they have given here. The decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. So N2O5 is decomposing like this one, it has been observed. Initially the concentration of N2O5 is 2.303. Okay, initial concentration is 2.303 mole per liter. After 184 minutes it is reduced to 2. So at time t it has been reduced to 2.08. okay, the reaction takes place according to the equation. Calculate the average rate of this reaction in terms of hours, minutes and seconds. What is the rate of production of NO2 during this process? How we will do that? How will do that? See, they are asking average rate of this reaction in terms of hours. Calculate the average. Average rate can be anything equal. For example, if I am saying A gives B, then minus dA by dt is the rate also equal to dB by dt, right? The same way I can do here, 1 by 2 minus 1 by 2 into delta N2O5, okay, N2O5 divided by delta T, that is the average rate, right? Average rate of this reaction. So delta N2O5 is given minus 1 by 2. Delta N2O5 is how much they have given? How much they have given here? From 2.303 it is becoming 2.08. So 2.08 minus 2.03 divided by delta T after 184 minutes, right? So first for 184 minutes we are doing 184. So if you are doing that here, see here, that only they have did here, right? So you will get this one. Now you have to do according with the like they are asking for hour, minutes and all, right? If you are doing the minutes, you just convert this 184 into minutes. So do into 60. So you will into 60 you will get in like which one? Minute. And if you do again into 60 minute also you convert to hours, sorry, second, then you will get in second also. So it may be remember that rate is equal to 1 by 4. Okay, see, based on the 1 by 2 with respect to NO2 it is 1 by 4. So like we have to find what is the rate of production of NO2. See here I am again saying that minus 1 by 2 into N2O5, rate of N2O5 into delta T, okay, delta N2O5, delta should be outside this one, will be equal to, according to NO2 it is 1.1 by 4 into rate of NO2, right, divided by delta T. So what will happen? We already found this quantity, right? Okay, we already know this much. How much it is? 6.79 into 10 to the power minus 4 it is coming. Okay, this is this one. Okay, this is this one. We already found. Now we have to find what is the rate of production of NO2. Rate of production is this only. See, this all is rate of reaction, but rate of production we know that is plus NO2 divided by dt, right, or delta T. Okay, so that will be, you take the 4 here, take the 4 here, so that is a 4 into 6.79 into 10 to the power minus 4. That's what they have did here. So now today we will stop from here. Again we will starting from the factors influencing rate of the reaction in the next session. Okay.